All right, everyone, welcome back to class. Go ahead and get settled. Let's dive right into today's explainer module. We are tackling Module 9, Responsible AI Architecture. As future engineers, it's just not enough anymore to build an AI that works. We literally have to understand how to architect systems that we can actually trust in the real world. So here's our roadmap for today. We're going to cover the generative paradigm shift, map out AI fault lines, and really dig into the alignment challenge. From there, we'll pivot over to practical engineering, looking at how to architect trust, the governance tool stacks you'll use, and continuous AI operations. Okay, kicking things off with Section 1, the generative paradigm shift. To really understand the risks we're dealing with in modern AI, you kind of have to unlearn how we used to think about software. Traditional software is deterministic. Think of it like a standard calculator, right? You put in input A, and you get a highly predictable, perfectly consistent output B. Errors are contained. But generative AI, it completely flips the script. Your input goes into a massive probability engine. It doesn't follow a strict predefined path. Instead, it generates totally novel outputs based on incredibly complex statistical weights. It acts a whole lot more like a wildly creative writing partner than a reliable calculator. So definitely make sure you get this definition of non-deterministic down in your notes, because these models act as probability engines producing novel outputs. They mathematically amplify the consequences of errors, biases, and unintended behaviors. Yes, it brings absolutely unprecedented creativity to the table, but that unpredictability, it introduces entirely new classes of risk that your standard traditional debugging simply cannot fix. Which brings us directly to Section 2, Mapping AI Fault Lines. Think about it like this. When a non-deterministic system is put under extreme stress in a real-world deployment, where exactly does it break? Well, it tends to fracture along three specific structural vulnerabilities. If you're the one engineering a generative system, you absolutely have to assume that pressure will cause fractures along these three fault lines, unless you deliberately reinforce them. Let's break those down. First up, systemic bias. Look, this isn't just a social issue, it's the literal mathematical reproduction of historical inequalities that were baked right into the training data. Second, hallucinations. This is statistical plausibility disguised as factual truth. It's exactly like that one student in a seminar who confidently makes up historical facts just to sound smart. The model is guessing based on patterns, it's not looking up verified knowledge. And third, harmful content. These are outputs that outright violate usage policies, violent, abusive, or discriminatory stuff. If you're building for high-stakes domains like healthcare or law or education, a failure in any of these three areas can be totally catastrophic. But beyond just the operational failures, we crash right into some very murky legal waters. Let me pose a question to the room. If an AI is trained on the past to generate the future, who actually owns the output? This is what we call the intellectual property dilemma. Think about the data flow. You've got your training data, books, images, source code, basically everything from the past. This flows right into the generative AI system, which acts as a bridge to output completely new text or media, the future. The dilemma is the massive legal uncertainty around fair use versus outright copyright infringement. Who owns that new creation? If you get this wrong as an engineer out in the industry, your company is staring down the barrel of some massive lawsuits. So to mitigate this, we really have to rely on licensed or open datasets, totally transparent sourcing, and robust output filtering. Let's move on to Section 3, the alignment challenge. This is essentially the core engineering problem of keeping these systems behaving according to our actual values. Think of it almost like a physics problem. You set an intended human goal for the system, right? But over time, across countless iterations, the model naturally wants to drift away from that goal. We call this model output drift. It happens because of intent mismatch, or maybe malicious users throwing adversarial prompts at it, or just general statistical decay. Alignment is the continuous active process of applying corrective forces, safety constraints, aggressive monitoring to basically clamp down on that trajectory and force it back toward human intentions. So, how do we actually do that? That leads us right into Section 4, Architecting Trust and Mitigation. Now it's time to shift from analyzing the problems to actually engineering the solutions. And the key here is a multi-layer mitigation architecture. You cannot, under any circumstances, rely on a single line of defense. An incoming user prompt has to pass through multiple concentric defensive barriers before it ever generates a filtered output. It's the classic concept of defense in depth applied to AI. Let's walk through these layers from the inside out. Step 1 is the core. This is about right-sizing and fine-tuning your models on carefully curated datasets so your baseline risk is as low as possible. Then we hit Step 2, prompt engineering and grounding. This is where you'll often see RAG used, retrieval augmented generation. That basically forces the AI to rely on external, strictly verified facts instead of just making a statistical guess. Moving out to Step 3, we introduce active safety systems, like moderation filters that identify and block harmful inputs in real time. And finally, Step 4 is the outer shell. That's your UI and UX design, which restricts risky behavior from the user in the first place. Every single layer compounds to protect the end user. Moving right along to Section 5, Tool Stacks and Global Governance. How do we translate those beautiful architectural principles into actual deployable software? Well, you use a specialized tool stack for safe AI. You're going to want to note these specific mechanisms. We use content moderation APIs like OpenAI's Moderation API or Google Perspective to automatically filter out toxicity. We use bias detection tools like IBM's AI Fairness 360 to mathematically evaluate our outputs for any demographic disparities. We implement privacy mechanisms, stuff like differential privacy, which injects controlled noise so that sensitive training data can't be exposed. And finally, you have to have monitoring and logging systems running to track post-deployment behavior for that statistical drift we talked about. But software doesn't just exist in a vacuum, right? It exists under the law. We have to look at the two major global governance frameworks that are currently shaping how we deploy AI around the world. The fundamental difference you need to grasp here is their approach. The EU AI Act is strict regulatory law. It uses a really rigid risk-based classification system, labeling AI systems as low risk, high risk, or totally prohibited. And it demands mandatory human oversight. Now contrast that with the US-based NIST AI risk management framework. Currently, that's a voluntary guideline. It focuses much more on an ongoing lifecycle process: govern, map, measure, and manage. As an engineer, whether you're dealing with Europe's strict tiers or NIST's process guidelines, you have to design systems capable of complying with both. And that brings us to our final section, the continuous AI operations loop. Let's bring this whole lecture home by focusing on the operational reality of deploying this stuff in the wild. You literally cannot just set and forget an AI model. Responsible AI operations require a highly dynamic, continuous cycle. You are constantly linking your monitoring systems to compliance standards, cross-functional collaboration, and incident response planning. You need contingency controls, like having a reliable kill switch ready to cleanly disable a rogue system the second something goes wrong. It requires constant coordination across your technical, legal, and operational teams. So, for your final takeaway, and definitely mark this with a star for the exam, here is the strict three-phase life cycle that is absolutely necessary for long-term alignment. Phase 1, monitor and log. You're continuously tracking the systems to flag any anomalies in user interactions. Phase 2, evaluate. You're regularly validating outputs for accuracy and safety compliance using automated metrics. And Phase 3, update and rollback. You must always maintain the capability to seamlessly update your models based on feedback or entirely roll back the system during a major incident. I want to lock in today's core lesson with this exact thought. Deploying generative AI is not a one-time engineering effort. It requires continuous coordination across technical, legal, and ethical domains to maintain trust and ensure long-term alignment. That right there is the absolute heart of what we are doing in this field. Responsible AI is an ongoing, interdisciplinary commitment. It never stops. So here is the big question I want to leave you with today. As you all step out into the industry as future engineers and leaders, are you going to build AI systems that merely generate outputs? Or will you take on the profound responsibility to engineer architectures that we can actually trust? Think deeply about that as you review your notes. Thanks for joining today's Explainer class. I'll see you all in the next module.